Hi everybody, this is Dr. Bricker here with a video for Chapter 25, Part 2. In this video we just cover Section 25.5. We're saving 25.6 when we do a little bit of modern physics and we talk about photons. Okay, so we've been talking about Faraday's law and how we can induce current to flow when we have a changing magnetic flux. So in other words, a changing magnetic field, changing angle between the magnetic field in the area or the actual area of the loop. So a changing magnetic field produces an electric field. So as it says here, what actually causes the current? What force pushes the charge around the loop? So from what we did before with circuits, we know that it was an electric field, maybe between the post of a battery, for example, or maybe it was the electric field caused by a capacitor could power charges to move. So it's an electric field. So a changing magnetic field actually induces an electric field. We talked about it in terms of it providing some amount of current, but what produces the current? Well, it's got to be an electric field. So a changing magnetic field ultimately causes current to flow because there is an electric field that's induced. So changing magnetic field, as it says here, creates an induced electric field. It's a little bit different, though, than the direction of the magnetic field, say, that a capacitor produces. So let's take a look at that. Okay, so in this picture you see an increasing magnetic field directed into the screen. So here's a magnetic field. The X's here means into the screen, and it's increasing. So an increasing magnetic field from Lenz's law, we would see that current would flow in this way, counterclockwise. So what's making the current flow? Well, we must have an electric field that's induced. Now the thing about the electric field that's induced, it's not in a direct line, it's in a circle. So the electric field that's induced is also circular like this. So it's a continual loop. So changing magnetic field produces an electric field, just like you see in the picture there. Okay, so an induced electric field is produced by changing magnetic fields, whether there is a loop there or not. So in this picture, you see that there's no actual loop. So you don't have to have a loop there to have an electric field that's induced. So changing magnetic field produces an electric field regardless if you have a conducting loop here or not. So just as a changing magnetic field produces an electric field, it turns out that a changing electric field also induces a magnetic field. This is a little bit less often seen, maybe, practically speaking, but consider if you're charging up a capacitor. So you start charging a capacitor, there's no electric field. The more and more you charge it, the bigger and bigger the electric field is. So charging a capacitor produces a changing electric field, and then a changing electric field would produce a magnetic field. So if you're charging a capacitor and the electric field goes from nothing to something, during that period of time you're producing a magnetic field. So if you had a compass around a charging capacitor, you would see that the compass needle would actually deflect while the electric field is actually changing. Okay, so we've got this idea of induced fields. Changing magnetic field can induce an electric field. This is what we've been talking about with Faraday's law, in the absence of any charges. So just a changing magnetic field produces an electric field. A changing electric field can also induce a magnetic field. But now you've induced a magnetic field, so now you've got an electric field. And then now you've got an electric field that's present, so you've got a magnetic field. What you get is a kind of a cascade effect. Changing magnetic field produces an electric field, then the electric field produces a magnetic field. This is essentially what an electromagnetic wave is, as it says down here. Electric and magnetic fields can sustain themselves free of charges and currents in the form of an electromagnetic wave. And it really goes back to Faraday's law. Changing magnetic field, you get an electric field, changing electric field, then magnetic field, so on and so on and so on. And that's what an electromagnetic wave is. We'll take a look at that in more detail in just a minute. So going back to this one, therefore it's possible to sustain magnetic and electric fields independence of charges. And I'll show you a nice picture of what this means in just a second. Let's see what the third one says here. A changing electric field can induce a magnetic field, which can change in just the right way to create an electric field, which can change to create a magnetic field. The fields are continuously recreated through electromagnetic induction. So let me show a picture of what they're talking about there. Okay, so we might have something like this. This is a conductor here. This is a positive side of a conductor. This is a negative side. However you've established that, maybe you've connected this to a battery or something. So there's an electric field associated with this. Now, if we can make the electric field change, a changing electric field produces a magnetic field, and so on and so on and so on. And maybe you're over here. Here's your eye, and you've got some kind of meter over here, and you want to figure out how the electric field is. Okay, so right now you could measure the electric field. It's kind of like a sort of like a dipole. Magnetic electric field goes out here, reaches your eye, comes back here. But now we're going to have a changing electric field. So this side was positively charged, this is negatively charged. But maybe this is connected to a battery, and you're just going to flip the battery around. You're going to make this side positively charged and this side negatively charged. Okay, so you've changed the electric field. A changing electric field produces a magnetic field. But you're over here, and here's your eye. You've got a meter, and you want to measure what the electric field is now. Well, it doesn't instantly change for you. This information has to come to you. That's what the electromagnetic wave is. That information is going to travel to you. The changing electric field produces a magnetic field. You don't instantly measure it over here. It takes some time for that information to get to you. That information coming to you travels in the form of an electromagnetic wave. You might guess this. How fast does it travel? Well, it travels at the speed of light, 3 times 10 to the 8th meters per second. And you're over here with a meter. You're trying to measure the electric field and the magnetic field of this situation changing. There's a certain distance here. If you're close enough, it might seem like it's instant, but it's not really. It takes some time. Now this oscillator here, you can continually change this. This is negative and positive. You can make this positive and negative just by flipping the connection to the battery, and so on. Keep changing it faster and faster and faster. That information takes some time to get to you. The changing electric field induces a magnetic field. Changing magnetic field induces an electric field, and so on and so on and so on. And that's what the electromagnetic wave actually is. That's what you're eventually going to be able to measure over here at your location. Okay, let's get back to the note. So what does it actually look like? Well, there's an electric field part and a magnetic field part, and it turns out that they have the same amount of energy. We'll see that in just a minute. And the electric field part and the magnetic field part are perpendicular to each other. So in the picture here, you can see that. So here's the electric field part, here's the magnetic field part, and they're always perpendicular to each other. And this wave is actually traveling this direction, here. Okay? So if you want to figure out the direction that it's traveling, if you take your fingers here, put them in the direction of the electric field, close them to the magnetic field, your thumb tells you the direction that it's actually moving. So the electric field and magnetic field part, again, same amount of energy. They have the same frequency. They're locked together like this. And the wave carries the electric field part and the magnetic field. To get the direction, close your hand from E over to B, and your thumb tells you the way that it's moving. Okay, so the wave here is a sinusoidal traveling wave, frequency F, wavelength lambda. So think back to physics 220, what these things actually mean. E and B are perpendicular to each other and to the direction of travel. So this is a transverse wave. The disturbance is up and down. The wave goes this way. And E and B are in phase with each other. They have the same frequency. One's a maximum, the other one's a maximum, and so on. Okay, very good. So that's some property of electromagnetic waves. Here's how fast they travel. The velocity of the electromagnetic wave turns out to be 1 over epsilon naught u0, the square root of that. So if you take these constants that you've seen throughout the semester, you saw this in the first week. This was from magnetism. Turns out the speed that the wave travels is 1 over the square root of that. So when you put this number in and this number in to this formula, you get 3 times 10 to the 8th meters per second. And that's what the speed of light is. So James Clerk Maxwell, Scottish physicist, the first to complete this analysis and concluded that light is an electromagnetic wave. People didn't know that at the time. They thought maybe you needed some sort of medium for the wave to travel through. People tried to come up with some analysis looking at it that way. But it turns out this wave will travel regardless if there's anything for it to travel through. So a sound wave, you need air in the room to hear a sound wave. If you took all the air out of the room and you tried to listen to a radio, you couldn't do it because there's nothing for the wave to travel through. Electromagnetic waves are different. They could travel through a vacuum. They don't need any substance to travel through. That's sort of a relatively new idea. This is from about the 1860s or so, this idea, this Maxwell idea. Okay, very good. So we know the speed that the wave travels, and we know a few properties. So if you take the electric field part and the magnetic field part from this formula here and divide them, you get the speed of light. So that's how these are related to each other. Now it makes it seem like the magnetic field part is really, really small compared to the electric field part. That's just a consequence of the units that we use. There's a set of units where the speed of light isn't there at all, and E and B are equal to each other. Completely different set of units. We're using SI units though, so E over B is equal to C. Okay, so electric field divided by magnetic field gives you the speed of light. And then don't forget what we did in Physics 220. The speed of the wave is the wavelength times the frequency. Initially we wrote it as the speed is the wavelength divided by the period, but 1 over the period is the frequency. So here's another way of looking at it. Okay, so we have some properties. We have some relationships here between E and B and the speed of light. So if you know E, you can easily calculate B because it's just related by the speed of light, and we know how much that is. So amplitudes of the fields, again, are related. This 0 here, epsilon naught and B naught, just means the amplitude. But you could pick any point along the wave, and whatever E is divided by B gives you the speed of light. But typically we talk about the amplitude, and the amplitude is the maximum amount the wave is. Okay, so this the plane containing the electric field, just by definition, they just picked it, whoever came up with this idea of E and B, maybe it was Maxwell, I'm not sure the origin of this. The polarization is the direction that the electric field vector points. Nothing special about it, that's just how they initially came up with it. This figure shows a wave traveling in the x direction, so the plane of polarization is the xy plane. In other words, where is the electric field part? It's in the it lives in the xy plane. So here's the xy plane, that's where the electric field lives. Okay, so it's vertically polarized because of the electric field part. The magnetic field part's going like this, the electric field part's going like that. And the wave is traveling in the direction, as you see here. That's the direction that it's going. Okay, so this one is vertically polarized because that's the direction of the electric field. This one is horizontally polarized because that's the direction of the electric field. This wave here, because this is the electric field part, the polarization is 30 degrees from the vertical. Okay, good, so turn like this. So each atom in the sun emits light independently of all other atoms, so the polarization of each atom is in a random direction. So you see a wave, the previous ones, oh, that was nice and clean. It was polarized horizontally or vertically. But the light that you see from the sun, all the atoms are emitting light. You're seeing a collection of the light that comes towards you. So the polarization of each atom is random. So the effect is, what you actually see is completely unpolarized light. So you're seeing light that has an electric field going in infinite amount of directions, as many directions as there are atoms in the sun. Now you can take unpolarized light and polarize it. We'll see how we can do that in just a minute. So the radiation from most sources is unpolarized. There's no set direction, but you can polarize it. And again, we'll see how you can do that with the filter in just a minute. Okay, so the energy of electromagnetic waves depends on the amplitude of the electric field and magnetic field part. We talked a little bit about this when we did sound back in Physics 220, Chapter 15, the intensity. So this is not current, this is intensity. So be careful, we've talked about current recently, but this means intensity. So it's the power divided by the area. And what is power? The units of power? Watts, or in other words, joules per second. So we have a certain amount of joules per second, and then this is the area that the wave lands on. So P is power, energy per second, measured in watts, and this is the area that we're seeing here. Okay, so just give a little summary down here. Power measured in watts, which is a watt is a joule per second. And just to remind you, and then the area here is square meters. Okay, so intensity, this part here, is going to be power, again, watts per square meter. But don't forget what a watt is, a joule per second. Okay, and so it turns out it's 1/2 speed of light epsilon naught electric field part squared, or 1/2 c mu 0 the magnetic field part squared. Now this looks pretty complicated, like there's a lot going on here, but don't forget, c is just the speed of light, it's a constant. Epsilon naught is also just a constant. So it turns out the intensity is really just proportional to the electric field part squared, also proportional to the magnetic field part squared. Now there's not a whole bunch of intuition in this formula. Maybe the power per area part, you have some intuition, but the rest of it you don't really. So it's, I think, beneficial, for me anyway. I like to write all the formulas down on a piece of paper, put a little note next to it, maybe draw a picture so you know what these things mean and how you're going to use them. Especially like intensity here. I mean, if you put this away, came back a week later, you might think, that must be current. Why is current power over area? So, keep everything straight and organized for yourself. Okay, now what exactly does intensity measure? So power is measured in watts. So pretend you have a 100-watt light bulb and you put your hands really close to it. All that power is over a small area, and that's pretty intense. So power over a small area, the intensity is really great. Now, the farther and farther you move your fingers away from this 100-watt light bulb, it's still a 100-watt light bulb. The power is the same, but the intensity is less because that power is spread over a bigger surface area. Okay, so that's the way to think about that. Okay, so the intensity of something like a laser beam does not change with distance. So the light bulb, the farther and farther I'm moving my hands away, the less and less the intensity was because it's going over a small area. That wave is spreading out. But a laser beam stays nice and concise. So if I'm close to it, the laser, or farther away, the beam doesn't spread out, so the intensity doesn't change. That's what it means there. The intensity of a spherical wave, which spreads out, that's sort of the light bulb example, decreases because I keep moving my hands farther away. So if the power source emits uniformly in all directions, as it says here, kind of like the light bulb, the wave intensity is power divided by 4 pi r squared. This 4 pi r squared, it's still area. It's the area of a sphere, though. So area of a sphere. I think I forgot something here. Whoops. Yep. There we go. Writing without spell check's a little scary in this modern day world. Okay, so sphere, hopefully I spelled that correctly. So intensity, power divided by area, and the area turns out to be the area of a sphere, which is 4 pi r squared. Okay, that's not the same as a laser beam, though. A laser beam doesn't spread out. Okay, so let's see what this question is. To double the intensity of an electromagnetic wave, you should increase the amplitude of the electric field by a factor of. Okay, so how is intensity and electric field related to each other? Here's the actual formula, and I have it written down over here because these are hard ones to remember. C, this is epsilon naught, and this is electric field part squared. So this is epsilon naught, this is electric field part. These look similar to each other. This is the constant 8.85 to the minus 12th that we had before. This is the electric field part. So you make a note of that. So we want to double the intensity of this wave. Okay, so you want to double this. What do you have to do to the electric field? Well, a first guess might be, well, I want to just double it. But that wouldn't work out for you, because if you doubled the electric field part in the formula it's squared, that would actually give you way too much. That would make the intensity 4 times as big. So the intensity is proportional to the electric field part squared. And the constant of proportionality is 1/2 c epsilon naught. Okay, so you want to increase it by the factor of the square root of 2 if you want to make this twice as big. So let's see how that would work out. So if I want to make the intensity twice as big, what if I made this the square root of 2 bigger? And then when you squared it, then it turns out to be twice as big. Okay, so and the square root of 2 is 1.414 if you're wondering where these numbers are coming from. So the square root of 2, you'd have to make it a square root of 2 bigger, as I did here, and the square root of 2 is 1.414. Okay, So it's one of those relationships where intensity is proportional to the electric field squared, and you have to sort of reason it out. A good guess is let's double it. Okay, see what happens when you double it. You make it 4 times as big, so that doesn't work out. It has to be the square root of 2 times as big to get twice the intensity. Hopefully that makes sense. Okay, so electromagnetic wave is a transverse wave. This slide has a bunch of information about it. Here's how the electric field, magnetic field, related to the speed of light. Here's the speed of light in terms of the wavelength and the frequency. The only other thing I would put on here maybe is the intensity, power over area, and then just like we had on the last slide, 1/2 C epsilon naught electric field part squared, which is fine. And then if you wanted to, you could solve for the magnetic field, the electric field in terms of the magnetic field, plug it in here, and when you do that, you get this relationship, 1/2 C over mu 0 and the magnetic field part squared. Okay, so this slide is a nice synopsis of what we've done so far today, actually. Okay, and this is the other piece of it then. Okay, so a nice little synopsis. Okay, so inside the cavity of a microwave oven, the 2.4 gigahertz electromagnetic wave has an intensity of 5 kilowatts per square meter. What is the strength of the electric field? And what's the strength of the magnetic field? Okay, so first of all, this just describes the wave. We're not going to actually have to use that in this problem. This is the frequency, though. So they're giving you the intensity. That's what this is. And they're asking you for the electric field and magnetic field. Now, again, this formula looks complicated, but this whole part and this whole part only has really one variable. This is the electric field that we don't know. C and epsilon naught are constants. Same thing over here. Okay, so the intensity from what we have here, 1/2 C epsilon naught electric field part squared. So you just have to solve for the electric field part. So multiply both sides by 2. Hopefully this is going to look okay. Multiply both sides by 2. Divide by C epsilon naught. And that will give you the electric field part squared. So then I've got to take the square root of both sides. Okay, so that gives you the electric field part. Be careful, this is 5 times 10 to the 3rd watts. Once you have the electric field part, you can get the magnetic field part. So this is how I would do the first thing for the electric field part. And then to get the magnetic field part, remember we had E over B is equal to C. This is to get the magnetic field part. So E divided by the speed of light will give you the magnetic field part. Okay, so you'll need this from the first part. And again, I should write the amplitudes there. Okay, there we go. All right, great. This problem is similar to 2533 on the homework. A digital cell phone emits 0.6 watts. Okay, 0.6 watts. That's the power. You can tell that because of the units. So the power is 0.6 watts of 1.9 gigahertz radio waves. So that's the frequency. What are the amplitude of the electric and magnetic fields at a distance of 10 centimeters? Okay, digital cell phone emits 0.6 watts. We want to know the amplitude of the electric field and magnetic field 10 centimeters away. Okay, let's take a look at that. Okay, so if we can get the intensity, then it's a short move to get the electric field and magnetic field. Because remember, if you know the intensity, just like the previous example, it's proportional to the electric field part squared, proportional to the magnetic field part squared. So the key is to get the intensity. So we're assuming that this digital cell phone emits this power in all directions. So we can get the intensity from that. Intensity, power over area. So power, given in the problem, I can write it off here to the side, 0.6 watts. And in the area, you'll have to figure out what the area is. And we're assuming that it's going in all directions uniformly. So the area is 4 pi r squared. So this cell phone's emitting in all directions. So here we'd have 0.6 watts and then divided by 4 pi, and the distance from here 10 centimeters. We need that in meters, so divide by 100, 0.1 meter, and then don't forget to square it. And then you have the intensity. And then once you have the intensity, you'll have to do a little bit of algebra, just like the last problem. You can solve for the electric field part. So just to remind you, that was 1/2 C epsilon naught electric field part squared. So once you have the intensity, you'll have to do a little bit of algebra, just like the last problem, to get the electric field part, and then you can get the magnetic field part. Okay, so that's similar to 2533. Oh, okay, so it's actually worked out here for us, but that's the reason why. Okay, great. So it turns out to be 4.8 watts per square meter. That's the intensity. And then once you have the intensity from the formula, do a little bit of algebra to get the electric field part. And then the easiest way to get the magnetic field part, it's the electric field part divided by the speed of light. Whoops. Okay, excellent. So the electric field amplitude reasonably small for comparison. Typical electric field due to atmospheric electricity is 100 volts per meter. The field near a Van de Graaff generator is 1,000 times larger than that. So this seems reasonable. It's not even get a huge number. The magnetic field's even smaller, and this is 1/250th of the Earth's magnetic field, which is really kind of weak. So you haven't really probably noticed any magnetic effects while you're talking on your cell phone, and that's the reason why the field associated with it is really, really small. It's there. It's not zero, but it's small compared to the Earth's magnetic field. Okay, great. So now you can transform unpolarized light. And unpolarized light is light that doesn't have a set direction, like from the sun, for example, by using a polarizing filter. So this typical filter that you see here is a plastic sheet containing long organic molecules called polymers. Okay, so here's the polymers, and then here's this is called the polarizer axis. So any part of the unpolarized light that comes in, so let's just pick one for example. This part comes in. It's going to hit this polymer, and we're going to take it out of the wave. Okay, so its energy is going to be used up by the polymers here, making them oscillate back and forth, things like that. So then you don't have any wave that's going to be transmitted through this direction. And this wave here, let's pick this one now. Maybe I'll try a different color just to keep it clear here. Green might not be the best. Oh, it might be okay. So this one also has a component that is this direction. So this component's also going to be eaten up by this the polarizer. This wave here, the horizontal one more color. This one here does not have any component that's this direction. So that one doesn't have any component that's up and down. So this one slides right through. And go back to the green one. The green one had a flat part here, and that's going to make it through. So anything that's perpendicular to this to the polymers here are going to actually make it through. And then what you get is polarized light. So that's the part that's actually making it through. The polymers there are sort of eating up any part of the wave that has any component that is up and down, and what makes it through, that's the part that still lives on. So the polarizer axis, as you can see here, it's perpendicular to the polymers, and the polarizer axis tells you which part of the wave is going to make it through. Everything else is killed off. So again, the polarizer axis, that's what actually makes it through. Now, as you can see here, so as light enters a polarizing filter, the component of the electric field oscillating parallel to the polymers drives electrons up and down, absorbs the energy, and that does not make it through. The part that makes it through is this part. Okay, excellent, and this really works. If you have a chance to take a look at the study area in Mastering Physics, and you go to chapter 25, there's a video of the lab assistant there showing you a demonstration. It's kind of a nice video to check out. Okay, so when polarized light approaches a polarizer, the magnitude of the electric field of the light that's actually transmitted is the transmitted amount turns out to be the incident amount times the cosine of the angle. And this is Malice's law for transmission of polarized light by a polarizing filter. This is the intensity. So this is the electric field part. Here's the intensity. And it turns out to be the cosine of theta squared for the intensity. That's because in the formula, the intensity goes as the electric field part squared, so you end up with the cosine of theta squared. So I guess that's maybe a little bit confusing. We were just talking about taking unpolarized light. This is polarized light coming in. So you're taking polarized light and you're putting it through a filter and seeing what you get out of it. So this already has maybe gone through one filter. It's polarized light at this point, and now it's hitting another filter. We want to see how much of polarized light makes it through. So this theta here is the angle between the electric field and the axis of the polarizer. So when the angle is 0, when light comes in, say this way, and the axis of the polarizer is this way, it all makes it through. And the cosine of 0 is 1, so you'll see that it all makes it through. On the other hand, if the filter axis is like this and the light comes in like this, nothing makes it through. Those are 90 degrees to each other. Cosine of 90 is 0. Okay, actually here's the link I was talking to you about. Let's take a look at. Okay, here's the video. Okay, so the sound didn't translate over when I played the video, but basically this is a microwave source, and the signal is polarized up and down. That is a speaker, and the signal is going to be received by the speaker, so when he turns it on, you actually hear a static noise happening. Okay, and what he's trying to do is stop that signal from happening. I mean, he's going to keep the thing on. He wants to block the signal out. And the thing that looks like a grill top here is a polarizer. So his goal is to block the signal out. Which way is he going to have to orient this filter to block it out? Would it be like that to block out the signal? Or, I think he's going to talk about it in just a second, would he have to rotate it like this? If he rotated it like that, would it block it out? Or would he do it at 45 degrees? Okay, so think about it. You want to completely eliminate the signal. The signal that's coming in, the electric field part is up and down. It's already polarized in that way. So you want to eat up that part. So you want this to be sort of lined up with it. Let's see what it says here. How should I orient the grill wires to block the signal? So you want them to be up and down, just like the signal that's coming out, and then you will essentially kill them off. Okay, let's take a look at it and see. Oops. Okay, so if you happen to have a chance to watch the video with sound, you'll see that there is no more static noise when he has it like this, because it's taking the signal. The atoms are. This shouldn't do anything. There's nothing. There's no way to kill it off. It stays the same. Now at 45 degrees, you'll kill some of it off. You'll be killing off a little bit of the signal here. So you could use the formula to figure out how much. The angle between the incoming waves and the axis of this would be 45 degrees, cosine of 45. So here's maybe a better picture of the orientation between the polarizer axis here. So if you have an electric field that comes in like this, this E cosine theta part, so here's theta, that's the angle between here and the electric field. This one over here is E cosine of theta. Okay, so maybe that makes a little bit more sense when you actually see that. Okay, and then the intensity, as you saw from the formulas we did before, depends on the square of the electric field. So the intensity was proportional to the electric field parts squared. So the transmitted intensity of the light of a filter comes from Malice's law here. So the intensity that's transmitted is equal to the intensity that's incident, and then the cosine of theta squared. And that's just purely mathematical from the electric field part. And then you can check out the homework help video to take a look at that. Okay, so how might you actually do this? Well, unpolarized light could come in from the sun, or maybe you have an incandescent light bulb or something like that, and you want to polarize it. So you send it through the first filter here called the polarizer. So you're taking unpolarized light. This is unpolarized light from the sun. You put it through one filter called a polarizer, and then now you've got polarized light, and use another filter called the analyzer here. And now the analyzer, you'll get whatever you want out of it. Maybe you want light that's completely vertically polarized. So you take this, send it through. You take this, send it through the analyzer, and you get the kind of light out that you want. Okay, so first one, polarizer, taking unpolarized light, polarizing it, and then the analyzer will give you whatever kind of light out that you want. You could actually completely block it all the way if you wanted to, if the angle between the axis and the light is 90 degrees, you can completely block it. You might want to block light sometimes. Okay, good. So here's a couple of filters here, and the lines here to show you the axis of polarization. So when a polarizer and an analyzer are aligned, the transmission should be 100%. You're completely allowing things to get through. This is the extreme case. You polarize light this way. You polarize light this way. This is the first one, and then you send it through another. You polarize it this way. You send it through another one at 90 degrees. Nothing is transmitted. So you've completely blocked out all of the light when you do that. Okay, so this is a cross polarization scenario here. So you've taken unpolarized light, you polarize it this direction, now you send it through the analyzer with the axis is this way, nothing makes it through. Okay, very good. So one time I was trying to read something from my cell phone, actually, and I had just gotten some new sunglasses, and I was sitting on my porch, and it was a sunny day, and I looked at my screen, and it's completely black. I could see nothing from my screen, and I asked my son, he's better with technology than me, and he couldn't figure it out. He looked at the phone. It turns out the light coming from my cell phone was polarized. I had polarizing sunglasses on. I had this scenario here where the light was at 90 degrees and I wasn't seeing anything. And I think it was just a fluke. Later on, the sun went down. I took my sunglasses off and I could see the screen perfectly well. So I thought I had a phone failure when really I was getting polarized light from my phone, looking at it with my polarized glasses, and then I wasn't seeing anything. Okay, so polarizing sunglasses, it says here, the axis is vertical, so light is only transmitted vertically. Why would you want that? Well, you're trying to eliminate glare. So say you're driving down the road, light hits the road, reflects back up in your eyes. When it's coming off the road, it's some component like this hitting you right in the eyes. That's what the road does to light. You want to block that, so you have polarized glasses on that doesn't allow that to come through. So as it says here, glare is the reflection of light from lakes, horizontal surfaces like the road. You want to block that only because you don't want to see it. It's kind of blinding sometimes. So that's the purpose of polarized glasses, to reduce the glare. Okay, and this section, 25.6 and 25.7, we're going to come back and talk about that when we do modern physics, when we talk about photons. Okay, so that's the conclusion of what we're doing for chapter 25 at this time. If you have any questions, just email me. I'll talk to you soon.